All right, so let's talk a little bit first about what a logarithm is, because it sounds just like some crazy difficult math stuff to deal with. But a logarithm is the power to which a number must be raised in order to get a certain value. So I've got a couple examples here. 2 to the x power equals 16. All right, what number would I have for my x right there? 4, right? Okay, so a logarithm is the power to which you must raise a number in order to get a certain value. So here we would say base 2, because 2 is the base of that exponent, right? The base 2 logarithm of 16 is 4. Okay, and if we wrote that in log notation, that would be log with a base of 2 of 16 would equal 4. So the exponential we should be pretty familiar with. We've done a lot of things with that. This is just saying what does that exponent need to be is not difficult for you guys. But if I had given you log base 2 of 16, you probably would have had a hard time telling me what that is based on what you learned before, right? 2 to what power should be 1024? Okay, 10, is he right? Because my brain calculations are not going to go up that high, but he's right. All right, so that means the base 2, right, because again, the base of our exponent is 2. Logarithm of 1024 is 10. So log base 2 of 1024 is 10. And let's make sure everybody is writing these correctly. When you're writing these, we almost need kindergarten lined paper here. If this right here is your line, the 2 is a subscript. It should be a little too close to the bottom. And 16 is a regular size letter, right? If we've got our kindergarten lined paper like this, that's what it should look like. Because what I sometimes find is I'll see kids writing it like this, log 2 16, 2 is my number and 16 is my exponent. This would not be right. That'd be a totally different thing that we would have here. So the base needs to be a little number written there on the bottom, and 16 is a regular size number. Sometimes we will put parentheses around that 16. Sometimes you don't. It has to be there if you're taking log of x plus 7 or something. But sometimes it's not written. All right, so what are some things that logs are used for? We're going to try to do some application with this. Time is our enemy right now, and I'd love to do more with it. But there are a lot of things logarithms are actually used for in real life. I'm not saying that your parents use them to do their taxes every year. This is not everyday common knowledge. But there's a lot of areas in science in particular, or data analysis, where this is used. The Richter scale is one, although as I was looking up about the Richter scale, I learned that the Richter scale is actually an older scale. We always talk about, if you hear about earthquakes, you probably talk about the Richter scale. But we actually use a slightly different scale these days that is called the moment magnitude scale. Because the Richter scale actually does not measure really strong earthquakes very well. We use the moment magnitude scale, although I think that they pretty much still call it the Richter, people still call it the Richter scale, even though it's not the Richter scale anymore these days. But if you hear modern scientists talking about this, they would be using this one. The decibel scale is another one that you're going to have. So that's noise intensity. So whenever you're talking about the amount of decibels that you're experiencing, that is on a logarithmic scale there. It's used a lot in data analysis when you have really large numbers. Basically down here, my last one, anytime you get really large numbers, exponential kind of growth, it may be sometimes helpful to look at that logarithmically instead of just with the straight numbers for that. So these are all different instances that hopefully we'll get to look at. There's a whole section on application and stuff that we'll get to, and we'll do some regressions and stuff like that. So these are all applications that you might see. Let's talk about logs as inverses. A logarithm is the inverse of an exponential function. Okay, so here I put, just as we could write A plus B equals C, right? That's addition. That would be equivalent to saying A equals C minus B, right? Those two statements are equivalent to each other, right? It's really the same equation being written in a different way. We do this a lot with lines. Like, for example, if I had like 2x plus 3y equals 4, that's called the standard form of a line, right? But a lot of times we don't want standard form of a line. We want y equals mx plus b, right? So if I solve that for y, I would subtract my 2x and divide by 3. So I'd get like negative 2/3 x, plus 4/3 there. Those two are equivalent to each other, right? If I graph them, it graphs the same line. So logs and exponentials are going to be the same, okay? If I have the exponential form of an equation, b to the a power equals c, right here. And specifically, I use the letter b right here because we call this right here the base. That is the base of our exponent. We also call it the base of our logarithm. A and c, just are other letters that I chose to use. But specifically, I use the letter B there because we typically call that the base, right? So if I have B raised to the A power, then that will equal C. But if I have log base B of C, it will equal A. These are equivalent. So you probably learned this like formula and used it. Now, one thing I like to do for this here, and I think I've got it on the next slide. I don't think I need to do it here. Let me see. Make sure. Okay. Now, this is important for you guys to know. Okay. If I do an inverse of a function, right, then they just cancel each other out, right? If I do x plus 2 and then minus 2, right, you just get x, right? So if I take log base b of b, those essentially just cancel each other out and equal 1. If I do b raised to the power of log base b, right? So I have an x, so this is the log of the same number. This is a, and I could, even if I might should put like an exponent of 1 right there, that's why that equals 1. If I do a base raised to a log with that same base power, those essentially just cancel out and give us 1, right? So, if I have log base 4 of 4, what is that going to give me? They basically just cancel each other out. The exponent on that 4 right there is 1, so we'd just be left with 1. Right? If I've got 2 to the log base 2 of 5, what happens with that 2 being raised to a log base 2? Those cancel, and I would just have the 5 for that. What do you guys think I'd get for 3? X plus 5. Okay? You, for this, have a couple options on how you want to deal with these problems. Because we know b, we put on another slide, right? B to the a power equals c. That converts to log base b of c equals a. So probably Coach Wood and Miss Martin or Mr. Brown, probably said, well, obviously this right here is my base, right? So I'm going to have log base 5 of 25. This number over here has to be the whatever was the whatever it was equal to, the C right here has to come over here with the log, right? And then that 2 will go over there. Okay, and that gets you the correct answer. Let me show you another. It's really, your answer is going to be the same. It's just a different way of thinking about this. If I want to make this into a log, the base of this right here is 8, right? So if I did log base 8 of both sides, what would happen if I'm doing log base 8 of 8? They would cancel, and I would just have a 3 over here. And on this side, I'd have log base 8 of 512. Now, other than my 3's on the left side instead of over here on the right side, which doesn't matter, I could switch those, right? It's the same, because 8 was my base on my log, 512 went over there with it, and then it's equal to 3 for that. You always have, like, whenever you do like the log of both sides, you want to do log with whatever number was the base of your exponent. But as far as like whether you think of it as a inverse or think of it as using that formula, it doesn't really matter. I do think the inverse is a little bit easier to think about when we start getting to the more complicated equations, but either can work. So if you're thinking of it sort of like I think of it here, I see 6 as my base. And if I'm trying to change this to a log, I'm going to do log base 6 over here, which will just cancel that out. And then I'll do log base 6 over here. So I will get, on this side, I just got an X. Over here, I got log base 6 of 125.
Could we just think of it as switching, like, where the equals?
You can.
Like the middle of the side?
Yeah. It doesn't have to be. What's probably going to happen on this is it's going to be multiple choice, and it could be written like this, or it could be written like this, log base 6 of 125 equals X. So we just know we can switch those sides of the equal sign. So either way is perfectly fine. Okay, so if we are rewriting 7, 8, and 9 here, so the base of this log is 5. So if you're just using like the formula, the base has to become the base of the exponent. What would the exponent be? It'll be 4, and then it will equal 625. Right? So perfectly legitimate way of thinking about this. I like to do it this way. I've got a log base 2 right here. So to get rid of a log base 2, I can do 2 to the power on both sides. That 2 to the power will cancel that log. And I'll just have an 8 over here. And then that'll be 2 to the 3rd power over here. But if you're just thinking of it with the formula, 2 is your base of your exponent. 3 has to be the exponent. It is equal to 8. Right. So here, if I have a log base 7, if I do 7 to that power, that cancels out that log, and 7 to that power on the other side, X equals 7 to the 10th power. Or, again, if you write it this way, 7 to the 10th equals X, perfectly fine. Right? Okay. So rewriting is definitely something that you're going to need to be able to do. Particularly for the purpose of solving equations, which we will not look at quite yet, and for finding inverses. So let's move on to the next slide here. So there are a couple special logarithms, okay, that we have that are so common that we use them a lot. So they have been given their own special titles, right? So a log with a base of 10 is called the common log. So if you ever see a log written without a base, then it has a base of 10, right? So if we have a log without a base, then it has a base of 10. There is a button on the calculator for a log with a base of 10. So over here on your calculator, that log button right there, that's going to be with a base of 10. Whenever you click log, does yours look like mine? It just comes up with a parentheses. It is next to your 7.
Yeah, it
Comes with a parentheses. Okay, I think. Because so if you just hit that log button, it's not going to give you an option for putting the base in there. That's just the common log, right? The other one that we're going to see a lot is a natural log. In fact, by the time you get to calculus, any of the log stuff they give you is almost completely natural log stuff. So natural log has a base of E. E is that 2.17848, whatever. No, that's not right. Whatever it is. There. If you see natural log, it has an automatic base of E, even though it's not written. There's also a button for it. It's right below your log button. And so if you are using that natural log button, that has a base of E automatically for that. Okay? So what we're going to see here, if we're trying to rewrite these, they look like they don't have a base. But they really do have a base. So like this one looks like it does not have a base, but its base is 10 because it's not written there. So if we're going to rewrite this, a base is 10. So I could do 10 to the power here and 10 to the power here. It will cancel my log right here. I'll just have x equals 10 to the third. Or think about rewriting it. Either way, it's fine. Okay. What's the base on number 11? It's E. It's not written there, but it is E. So if I do E to this power here, that cancels out my log on this side. E to the power here. 4 equals E to the x, or E to the x equals 4. Okay. 12 is an exponential. Okay. Sometimes it might even be helpful to you to like use a log base E, but we just don't ever want to leave it a log base E, right? Because if you write something like log base E, you're letting me know you don't know what a natural log is, right? Because we would never write that. We'd write it as a natural log. So like to get rid of a log, or of an exponential with a base E, I would do log with a base of E on that side and a log with a base of E over here, which would cancel out this. So I'd have x equals log base E of 5, but we don't want to put log base E because log base E is just natural log, so it'd be natural log of 5. For that. So these are going to come up a lot. They'll be mixed in with all the other problems that you see. So we'll need to know about those. All right, now, this is something you probably were not asked to do in, Math 3, because this is evaluating without a calculator, okay? So if you have a calculator, and we'll look at next what to do with a calculator, these are very simple to figure out because you just type them into the calculator. But we have a calculator inactive section of our test, and we will be expected to know how to do the ones like these without a calculator. So if you are asked to do these without a calculator, I usually try to rewrite them as an exponential because my brain does not really know much about log base 2 of 8. Right? I don't have log values stored in my brain where I can tell you what that's supposed to be. But if I write it as an exponential, then it's really just like multiplication. And that I might know. So it's not an equation right now, but could I put equals x over here on the side to make it an equation? That's what we're trying to find, right? So if I write this as an exponential, right, I like to think of it as an inverse, or you can just rewrite either way. To get rid of a log with a base of 2, I do 2 to the power, which cancels that out. It just gives me an 8. And then I also have to do 2 to the power on the other side, so I get 2 to the x power. Now, 2 to what power would give me 8? 3. So x equals 3. So the value of this would be 3 for that. So if they give you something like this, it's going to be whole number answers or simple fractions that you're going to be getting for this. Okay. 14 doesn't have a base. What is it? 10. All right. It's got a little 10 hiding right there. I'm going to do the same thing I did on the last problem. I'm going to put it equals x because that's what I'm trying to find. So think about it either as rewriting or as inverses. To get rid of a log with a base 10, I would do 10 to the power. It would cancel. I'd do 10 to the power over here. I'd have 100 equals 10 to the x power. 10 to what power gives us 100? 2. So 2 would be our answer here. All right, here. All right, same thing for these others. To get rid of a log with a base of 16, I do 16 to that power to cancel it out. I do 16 to the power on the other side as well. I got 4 equals 16 to the x power. What's that? Nope, but you're thinking in the right direction. It's 1/2. Because 16 to the 1/2, fractional exponents, what do we use for those? Roots, right? And so this would be the square root of 16, and square root of 16 is 4 for that. Because it's 16 to the power, not 16 times that x, in which case it would be 1/4 for that. So that one's a little tricky. All right. Then, for this one, I'm going to put it equals x over here. To get rid of a log with a base 3, I do 3 to the power over here. I do 3 to the power over here. So I'll get 1 equals 3 to the x power. What's x going to be? 3 to the first power is 3. It's 0. Okay. In fact, log of any base of 1, right? If I do log base b of anything, that would be like b to the x power equals 1. It doesn't matter what your base is, right? The only way you can get 1 with a log or with an exponential is for x to equal 0. So log with any base of 1 always equals 0. That's a good thing to kind of have memorized, so when you see it, you automatically know it's 0. Okay, so if you're asked to do these without a calculator, you want to just rewrite it as exponential, and then in that exponential, you should be able to figure out what the exponent should be, because they should be whole numbers. But you're also going to see these with a calculator, and they're really pretty simple to do with a calculator. So you got 2 options for how to type these into the calculator. The first thing that you can use is called the change of base formula. These calculators used to not do a different base, and you had to do the log A over log B. So this is what I always do because it's what I did for a long time. Plus, I think it's a little easier to remember how to type it in if you just know the formula. But there is also an option to do a log with a different base if you go to the math menu. Also, I should have put this on here. It actually does not matter with your change of base formula if you use log or if you use the natural log button. So if you use natural log of A over natural log of B, it'll give you the same answer. Okay, so let's just do number 17. I'll show you what the 2 ways that you can do this. For 17, if you use the change of base formula, it is log of 5 over log of 3. Right? And so you would type it in like this, log 5. Now do be careful right here. If you use change of base formula, you've got to close that parentheses before you divide, or else it's trying to log everything there. And then log 3. And so we get 1.465. Just a note, a few of you were Some of you, I think, were not rounding correctly because on that last problem you were plugging in answers and you couldn't get close enough. But a few others of you just did not round to 3 decimal places in a few places on your test. Make sure, unless it tells you otherwise, you are always correct to 3 decimal places for that. So you want to keep at least 3. If you keep more, it's always okay. But you got to have at least 3. Don't round it off any less than that. Now, notice if I did natural log of 5 divided by natural log of 3, that would give me 1.46497, same decimal, right? So you can use either button, just don't mix them. It's got to be the same one. Now, there is also a log base that you can use on the calculator. So, actually, I don't even need to do that. What should I do for number 18? Just ln12, because there is a button for natural log, right? That button of natural log, you don't have to do anything special. If you're doing natural log of something, you just type it in. Same thing for a common log. If you have a log with a base of 10, right, you just have to type it in with the log. So this will be 2.485. And even though if you were just going overboard and did use change of base, if I did natural log of 12 divided by natural log of e, because e is the base there, it'd give you the right answer. So it doesn't hurt to do it that way. All right, let me show you the other way that you can do a base. You might prefer this just because it looks like it's supposed to, but you got to remember where it's at on the calculator because there's not a button on the panel for it here. You have to go to math. And if you go all the way down to A, it's going to say log base. Okay? So if you hit the math button, which is right underneath that green button, and you go all the way down to A, it's going to say log base. And then it will let you type in a base if you do it this way. So you got 1.3, and then over here you got 2.7, like that, and you'll get 3.786. So I don't care which one you use at all. As far as which way you type it in, you just need to know either the change of base formula or where to find that log base there. Okay, is that all right with everybody? Okay there? All right, let's keep moving. All right, tell me which one of these is exponential. This is not log stuff. This is old stuff. Okay, Tyler's telling me the third. How do you know? Okay, because you're multiplying by an amount, right? You're multiplying by 2, multiplying by 2, multiplying by 2. What have we got for that first one? What would that be? It's plus 2, so that makes it what kind of pattern? Linear. What about for the middle one? It's not, it's neither linear nor exponential. It is quadratic on that because this goes up by 1, that goes up by 3, that goes up by 5. But if you did a second difference, it's going up by 2. So that would be quadratic. But this one asks us for the exponential, right? So in an exponential, our x values are increasing just by a constant amount. It doesn't have to be going up by 1. It could be going up by 2s or 5s or 7s, but it has to be going up by an equal amount, right? And our x values are being multiplied. So because exponentials and logs are inverses, this is going to switch whenever we're talking about a log, right? So our exponential equation is right here. That's the one we just picked for exponential, so I might should have labeled it. That one's exponential. Okay, so the inverse would be a log, right? So if I want to make a table for my inverse, what would I do with those? Just flip the columns, right? So 1, 2, 4, 8, and 0, 1, 2, 3. So this is going to be a new type of question they might give to you in a table, right? We've talked about linear, it has a constant rate of change. A quadratic That second difference is going to be constant. Exponentials, you can multiply by a number. Now they might throw logs in there as well. So in an exponential, the input values increase in equal intervals. So input values are increasing by that same amount. The output values increase multiplicatively. What's that crazy sounding word mean? You're multiplying by a number there. Multiplicatively. I hope I spelled it right. Don't stare at it too long. It might be wrong. Might be Ley. Don't know. Well, it's not important. They won't grade you for spelling on that. So in a log, the opposite is going to be true. So in a logarithmic function, the input values, your x column, should increase multiplicatively. While your output values increase in equal intervals. So basically, when you see a table that's supposed to be a log, you should see your x values being multiplied while your y values are just going up by a constant amount. Right? It's just the switch of an exponential for that. So let's try a couple. All right. Okay. So for these, we are supposed to determine if they are logarithmic, exponential, or neither. Okay. And we're particularly looking for our logarithmic ones. Which ones do you guys think might be logarithmic? 2 and 4. All right, so definitely on this one, we're going up by 10. We're going up by equal amounts on the y value. So here, 10 times 3 would give us, so times 3, right? Times 3 times 3. So we're multiplying for our x values, adding a certain amount for our y values. That is a log. Okay? And then you said also 24 over here. That goes down 3, down 3, down 3. Doesn't matter what that number is as long as it's a constant rate of change for your x, right? What would be happening for our x values? Times 2. Times 2. Times 2. So that is a log. It's not. Why is it not? Because definitely you're multiplying by 10, right? But you're also multiplying over here. I don't really know what that is if you're multiplying on both sides. It might have a name, but we're just going to call it neither for right now. And I don't think it's something we're going to look at. What about 21? Okay, we could multiply by 1/2 on that right side, right? And on the left side, you're just going up by 1. So what's that one going to be? That one's exponential. Okay? So being able to identify those from tables is something we'll be asked to do. Actually, the homework doesn't have any tables on it, but they will show up. All right. Now, let's work on finding inverses. Okay? The rules or the directions for finding inverses are the exact same as they were for all the other inverses that we have done, right? So if we're finding an inverse algebraically, what do we do first? Switch your x and y's. So where this is like our y, right? We will switch it and we'll have x equals log base 7 of x. Oh, no. Y. Oh, shoot. X equals log base 7 of y. We want to solve that for the y right there, right? Which means we've got to get rid of the log base 7. How do we get rid of a log base 7? we're going to do the base raised to that side, right? On both sides, right there. Or you can think of it as rewriting, whichever way makes most sense to you. But I like to think of it as inverses here. That cancels out. So we've got 7 to the x power equals y. And if we write that back with inverse notation, inverse of f is going to be 7 to the x power. Okay, you might want to take a guess about what 26 is going to be before we work it out. If log base 7 of x was 7 to the x, what do you think 3 to the x is going to be? What? Log base 3 of x, yeah. But if we work it out, we'll have x equals 3 to the x power. Be real careful here because you might be tempted to like divide by 3 on this. Oh, gosh. Why can't, shoot. Can I make that go back? Why can't I remember to do that? Right. All right. Yes, that'll be a y. Now, you may be tempted to like divide by 3, but that is not, that division is the inverse of multiplication, right? We're not multiplying, we're raising to a power here. So the inverse of a base 3 is log base 3. So we got to do log base 3 on both sides. So we get log base 3 of x equals our y. We could rewrite that with inverse notation. G inverse of x would equal log base 3 of x. Okay, let's look at a couple that are a little more difficult for this. I've got h of x equals log base 2 of log base 5 of x. So that's going to be x equals log base 2 of log base 5 of y. Okay, here's one of the reasons I kind of like to think of it as an inverse rather than think of it as rewriting. Because this one's complicated with like double logs right here, right? So which log would we need to get rid of first? The furthest away. So we want to get rid of the log base 2 first. I can get rid of it by doing 2 to the power over here, as long as I do 2 raised to the x power over here. So that will cancel. I will have 2 to the x equals log base 5 of y. And then I can get rid of my log base 5. How do I get rid of it? 5 to the power over here. We'll cancel that out. And then 5 to the power over here. So that is going to give me my y will equal 5 to the 2 to the x. But when I'm doing like powers raised to other powers, I can do that a couple different ways. I could do this as like 5. I could write it as 5 to the 2x if I want, or I can do the 5 to the second and then raise it to the x power, which is going to be probably the cleanest look for our inverse here. So we could say that that inverse is going to be 25 to the x power. It is also possible that they would do 5 to the 2x. It just depends on what they decide they want to leave it as. I like the 25 to the x power best there. Okay. This time we've got an exponential, but it's got more complicated stuff with it, right? So this is going to be x equals 10 to the 2y minus 1. So we have got to solve for that y on the right-hand side. We got to get rid of that 10 first, and it's not 10 times that stuff. It's 10 raised to that power. So how do I get rid of a base of 10? It's already an exponential, right? It's an exponential right now. So to get rid of an exponential, I've got to use a log. Okay? So I will do log base 10. Is that 10 necessary? It is not, because if I just don't write it, then it's just a regular log, right? A common log. So I got log of x equals 2y minus 1. And then I'm just solving for that y. It's just basically simple steps now. I just need to add that 1. So I got log of x plus 1. You don't have to put this here, but like the x, that plus 1's not inside of the parentheses there. You're just doing log of your x. And then that equals 2y, and I could divide by 2. So I will get log of x plus 1 over 2 equals y. So if I want to write that with inverse notation, k inverse of x would be log x plus 1 over 2. If, and you may see this on your assignment, if they do not have parentheses, with your log, assume it only goes with what's right after it. Now, if I have something like this, if I've got log 2x, it will go around that 2x. But if I have log 2 minus x, if there are no parentheses written, it only goes with the 2, right? If things are multiplied, it'll be everything together. But if it's added or subtracted, it's separated. If they want it to be log of 2 minus x, they'll put parentheses around it for that. So we just got a couple more little things here. All right, here. A portion of the graph of 2 to the x power is shown. I'm supposed to sketch the graph of log base 2 of x. What do I know about these two right here? 2 to the x and log base 2 of x. They're inverses of each other. What do I do with, if I'm trying to graph an inverse? Switch an x and y's, right? So like this point right here. Oh, shoot. Didn't mean to do that. This point right here will end up right here. So 0, 1 becomes 1, 0. This point right here is 1, 2. That's going to be 2, 1. This point right here is 2, 4. That'll be 4, 2. These are kind of hard to see. Like that's -1, 1/2, let's say. So that's going to be 1/2, -1, that'll be here. Let's call that like -3, -0.1. So -0.1, -3 right here. What happens, that graph right there, the exponential has a horizontal asymptote at the x-axis, right? When we flip this over that line, we're going to end up with a, excuse me, we're going to end up with a vertical asymptote at the y-axis for that. And so when we have graphs, and we're going to look more at what the graphs of logs look at on Monday, but that's what we'll have there. And then last thing, so that you can maybe do at least a couple problems. My exponential function is a to the x power. They didn't tell us what a was, right? But they did give us 2 points on that graph. And then they give us another graph, y equals log of a, log base a of x. And they want the average rate of change for this graph from 3 to 27. Whenever I go from h of x to log base a of x, those two should be inverses of each other, correct? So 2, 3, and 6, 27 are on the exponential function. What are those points going to be whenever they're on the log? 3, 2, and 27, 6. What's it asking for when it wants the average rate of change? Change in y over change in x. So we're going to use these new points. Change in y over change in x will be 6 minus 2 over 27 minus 3. So we will get 4 over 24. So 1/6 for our answer there.
And so we just ignore the 327.
3 to 27 is telling you what the new x coordinates are. So if there were like more points, like if they'd given you in a table, you would have to pay more attention to that. But it's telling you what the, like if we had a whole table with a lot, we'd have to look for those points once we had switched it there. All right, so your assignment is a worksheet. These hopefully should go very fast for you. It's just some rewriting and finding some exponent, finding some inverses. So hopefully it will be a rather quick assignment. I think you'll be able to get maybe even the front side done before you go. Yes. Okay, let me go get rid of the let's see.